Information Theory by Aaron, Jason, Richard, that's me, and Ian. Topics that will be covered includes Szilard's engine, Landauer's principle, and fluctuation theory. But first, we have to figure out what information theory is. Information theory is a study that revolves around the emission, processing, and extraction in information in topics including mathematics, computer science, and thermal physics. How do we try to get information? Well, we use probabilities like P of S, a statement, or P of Q, a question, without any prior information given to us. Instead of using probabilities, we can also use entropy, S, as a measurement of information as well, or we can call it Shannon's entropy, which we'll expand on later. Claude Shannon, a mathematician, proposed the definition of information in the following equation, where Q, the information, is equal to negative K log P, where P is the probability of a statement being true, K is a positive constant, and n is the base of the logarithm, which is the number of possible states that the statements can be true in. An example of this would be binary, where there's two states, 0, false, or off, and there's 1, true, or on, which the equation for information Q would be equal to negative K log 2P. If we had a statement with an arbitrary probability P and corresponding arbitrary information Q, where the equation of Q is equal to negative K log P, then the average information of each statement Q can be expressed as the value S, which can be expressed by a summation of I of Qi times Pi, which is the information times the probability, or also equal to negative K summation I of Pi log n Pi. This expression gives us S, which is also known as Shannon's entropy, or average information per statement. Therefore, when we measure the average information we gain for each statement, it's quantified by Shannon's entropy, which also determines the amount of uncertainty or the lack of information we have before measuring it. In thermal physics, we talk about this using microstates in class, which they can also be incorporated into the Shannon entropy equation, where S is equal to Kv, the Boltzmann constant, ln W, where ln is the log of E and W is the number of microstates.
So now we're going to talk about Szilard's engine. Szilard's engine is a thought experiment describing how the possession of information may have thermodynamic consequences such as entropy reduction. Szilard's engine is similar to the Maxwell's demon thought experiment, wherein a container of gas is connected to a vacuum and there is a closed tap between the two containers. Theoretically, the process of opening the tap and allowing the system to reach equilibrium with an equal volume of gas in each of the containers is an irreversible process. However, the existence of a demon capable of measuring the momentum and position of individual gas particles would violate the second law of thermodynamics, for example by inducing a flow of heat from a cold source to a hot one. Szilard's engine follows a four-step process. Initially, there is a single particle in a box. Then a partition is placed in the center of the box, trapping the particle on one side or the other. The work done to insert this partition is 0. The demon, which is in thermal contact with a heat bath, is able to determine which side the particle is on. The work done by the demon here is a function of the temperature of the demon. The particle then performs an isothermal quasi-static expansion using a load attached to the partition. The daemon, using the knowledge of which side the particle is on, is able to extract positive work from the system. From the ideal gas equation, we find that the total work that can be extracted is the temperature of the bath times ln of 2. Finally, to return to the initial state, the partition is removed and the load is removed. The work required for this step is 0. Excluding the work done by the daemon and focusing only on the mechanical work done in the system, the total work for one cycle in Sillard's engine is the temperature of the bath times the ln of 2.